recognize these materials radiographically so that you can treatment plan them properly, okay? So we need to do that. Also with the patient, when you're looking in there, so that you can assess and recommend treatment. Now, you're not diagnosing. You're just saying, I think the doctor's gonna say blah, 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 blah. The more the patient hears it, when you and the doctor say the same thing, then they think, oh, then I must really need this, okay? So, this goes hand in hand with educating the patient. Because while you're cleaning their teeth, you can talk about, you know, their family and all like that, which is great, because you want to get to know them. But you need to let them know, why do I need a crown on this tooth? Well, if you can't do a crown, what's second best, which is a restoration, okay? How long will that last? What if I don't do anything at all? Well, then you might lose the tooth. But it's their choice, but it's your job to give them all those recommendations. Okay, so we also want to know what material is good for replacement when we've lost hard tissue in the mouth, okay? Which would be teeth or bone, okay? And we want something that's biocompatible. So for example, with dentures, what's the pink? Does anybody know what that pink is? Acrylic. Acrylic is compatible with the tissue. It's wettable so that we can get good suction and it doesn't irritate. So we want something that's kind to the oral environment and compatible. We don't want something that's going to cause a rash, okay? Or something like that. So with a denture, we know that even though it's acrylic, oxygen isn't getting there. So we need to educate the patient on, please take this out. And some people don't, they want to sleep with their dentures at night because they don't want their spouse to see them with no teeth. Can you take them out sometime during the day? Let that tissue breathe. Honestly, if you just leave these in all the time, no matter how compatible this tissue is, if you don't take these out, it's like wearing your shoe forever. What are you gonna have? Stinky, moldy feet, right? So we want to be careful of that. Okay. Materials are classified. In 1976, the federal government, under the FDA, came up with the Medical Device Amendment, okay? And under this amendment, they regulated medical and dental products, okay? So regulation of dental materials is by the FDA, not the ADA. Federal regulation is FDA, okay? So class 1 are dental products that are least regulated. Prophy paste, what's in it? Hummus, a little bit of flavoring, that's about it, you know? Some silica, depending on how gritty it is. So that's one of the least regulated, and fluoride, okay? Now, there are some non-fluoride toothpaste out there, and guess what? They're not regulated. Non-fluoride toothpaste are not regulated because the government, FDA, considers them to be cosmetic because they don't have fluoride in them or a chemical in them, okay? Class 2 are a step above. So things like composite material and amalgams have to be approved by the FDA before they go on the market. And number 3, class 3, is the very heavily regulated items such as bone grafting material, implants, absorbable sutures, things of that nature, okay? Because they're important. They're used in more invasive procedures, okay? So that's how our items are regulated. Any questions about that? So 3 categories. categories. Now the ADA seal is different. Does every dental product have to have an ADA seal on it? Take a guess. No, it does not. The manufacturer chooses to go through the hoops to get that ADA seal because it means something to dental professionals. Okay, when they see that ADA seal on their product, it gives professionals a sense of comfort. Okay, so it's a second layer. So they evaluate the products and then they give it a seal of approval. And then every so many years, the manufacturer has to submit it again for approval. So you have to keep submitting it, okay? So, difference between ADA and FDA. FDA does what? Say it again.
Like regulation.
Regulation. ADA is
American Dental Association.
approval process, a non-mandatory approval process. Okay, so a lot of people think it's the ADA that guides those approval on the market, but it's really heavily regulated by the FDA, the government. Think of the government, right? Now, in Europe, they have the same thing. So if you buy a product and you see, have you ever seen symbols like this on your dental products? Anybody that's been in an office? That means it was manufactured overseas, okay? So a lot of our dental products are manufactured in Germany, Japan, China, okay? Those, Canada, Sweden, yeah. And those places. So their seal of approval is not the ADA, but the ISO. And so you'll see a symbol like this. Actually, dental film, which we don't hardly use anymore, a lot of dental film is manufactured overseas, so you would always see this. But now with sensors, we don't see that so much. All right. So I want to start with the properties of materials, and then I'll be going through the definitions. We have three categories: physical, and a subcategory of physical is mechanical, okay? We also have chemical, somebody's gonna slip on that, and biologic, okay? So those are our three categories. Oops. Okay, so what I want to emphasize is that all products don't meet physical, mechanical, and chemical. They don't have to, but they all meet different properties. So not all products need to meet all requirements, okay? It depends on what it's doing. So amalgam, we want strength. So that would be a physical or mechanical property. When we mix cements, it's a chemical reaction, so that kind of thing. Biologic is just the material itself, titanium implants. We want it to be biologically compatible. Starting with physical properties, and our first one will be, well, physical properties are mass, energy, force, heat, electricity, and physical things like that, okay? So again, we said that mechanical was a subset of that. So our first physical property is thermal conductivity. So it's the ability of materials to change, to adapt to temperature change and the transfer of heat. So materials are subjected to hot and cold things because we drink cold things and we drink hot things. So we have to be careful careful about that. What I want you to know is our materials are based on enamel and dentin. And enamel and dentin are poor conductors of thermal conductivity. Therefore, our products have to protect them by having protection against hot and cold, or there can be some problems, okay? And one of the problems that we have is dimensional change. So that's the shrinkage or the expansion of a product, okay? This is very concerning to us with restorative materials, amalgam and composites, for example, because they're placed in the tooth, and if they expand and contract too much, we have a problem, and I'm going to talk about that problem in a minute. And if we have a problem, then we have pain. Patient has pain. So we want to avoid that. So the deal is we want to try to maintain that dimensional stability. Same thing with impression materials. If we have too much expansion and contraction, we've yanked on it, we pulled it out too soon, the impression material, it's going to play with us. And then if we go to make an oral appliance or something, it won't fit because of dimensional instability. So, okay. So the coefficient of thermal expansion is this. Amalgam and composites have a higher coefficient of thermal expansion than the tooth does. That means it will expand and contract more than tooth. So as the operator, when we're placing it, we have to be careful in our placement, condensing the amalgam, curing the composite a certain way to avoid or minimize expansion and contraction as much as possible. Porcelain, which is a material we use on crowns a lot, is less than. So that's nice. Put that over. So we don't get that expansion and contraction. Okay, so what happens when we get expansion and contraction? Okay? Well, when we drink cold things, the composite or the amalgam, mostly composites in this case, will shrink. That leaves an opening, okay? So that opening allows food and bacteria, hot and cold, to go in and out. So if I eat a cold ice cream cone and ow, I have a mouthful of restorations. I got some expansion and contraction going on. That is called percolation. Moving in, moving out. Bacteria. Because there's now a space, and it's microscopic, you can't see it, that's open, and the result is that hypersensitivity, okay? So how many people are sensitive to cold things? Yeah, raise your hands. When the temperature goes back to normal, what happens? Oh, everything's okay again, okay? So, when we have percolation, we have movement of fluid in and out of the space between the dental restoration and the cavity wall. Gee, that's in bold. I wonder why. Might I see it on a test? I could. Okay, that's called marginal breakdown. Okay, so we can have marginal breakdown over time. You have probably seen some restorations in clinic where the margins are open, right? Where they're not smooth. Maybe you have yet, maybe you haven't, I don't know. So that we want to avoid. Okay, so the coefficient of thermal expansion, you don't need to memorize these numbers, just it's up there for comparison. So a tooth, its coefficient of thermal expansion and contraction is 11.4 points per million times 10, okay? Just think 11.4. Direct gold is 14.4, so that is the material that is closest to amalgam, or to tooth, I'm sorry, gold. Which is why, back in the day, we always used gold for our crowns and bridges and inlays and onlays. We don't use gold so much anymore. Number one, it's too expensive. Number two, people want cosmetic teeth. Old people still like gold. I know. And young people. Some of us still like gold because we know the difference. Okay.
So with percolation, that's the movement of fluid in and out of the space. But percolation then results in that marginal breakdown because there's that space.
Yes.
Okay, I just wanted to make sure. I was
Yes.
on
Did
the
everybody
same.
get that, understand that? Okay. And then we have amalgam, which is less coefficient of thermal expansion is less than composite, and then unfilled resins. So an unfilled resin, we don't use those anymore. Most of the composites that we used are filled, but that is just an old graph that I took out of your book. Okay. I wanna say, I think I said enough. Okay. So galvanism is an electrical property. I know it's under physical, but it's an electrical property. And this is when you have two dissimilar metals together. It can be a gold crown and an amalgam, could be a silver crown, tin can crown, and a gold crown, something like that. And it creates a galvanic shock. Have you ever been on foil? And you get that feeling? Well, if you haven't tried it tonight, you'll know what I'm talking about. It's not fun. Yeah. So anyway, sometimes, and this was back in the day when we did do a lot of gold work, and gosh, there was an amalgam next to it. We put in the gold, the patient would call and go, oh my God. So what we would say is, eat acidic things. Eat a tomato to try to minimize that galvanic reaction. If it didn't work, what do we change? The gold crown or the amalgam? We had to do something. Didn't get any better. What do we have to do? I'm the dentist. What am I gonna do? Yeah, you're gonna change the amalgam to a composite filling or restoration. Because composite is not a metal, so you're not gonna get that galvanism, okay? So, and I just said the word filling and I could hit myself for saying that. So in private practice, you would use the word filling because that's what patients hear. But when we're talking to each other or you're talking to a professional, you wanna say restoration. When you get out in private practice, you'll be back to filling, but filling is in pie, not in your teeth, okay? That's what I was taught by Dr. Holliday way back in the day when I was a student. Filling is in pie, not in restorations. Note to self, he'll run over me going down the parking lot.
Sometimes I can have many more. Like people will get that's their restoration on the part.
Yep, got a brand new one until it kind of tarnishes a little bit. Yeah, we'll hear about tarnish. Okay. Oh, guess what? We're going to now. Corrosion and tarnish, which is electrochemical. Now, corrosion is the action that affects both the appearance and the strength of the metal. It's a pitting and dulling of the amalgam, and it cannot be polished or it is not irreversible. So when you see a restoration that's very dark and black, and it's kind of broken down or pitted a little bit, that's corrosion. Tarnish is a surface reaction. You tarnish before you corrode. It can be finished and polished with amalgam polishing, which we'll talk about that, but we're not actually gonna do this year because nobody does it anymore. And it is reversible. So sometimes tarnish and corrosion look alike, but please know the difference. Corrosion is surface, subsurface, pitting, and you can polish the heck out of it and not get anywhere, okay? Tarnish but less expensive form and can be finished and polished. Like your silverware tarnishes, it doesn't corrode, it tarnishes, so you get out your silverware cleaner the day before Thanksgiving and polish that stuff up for mama, okay?
Sue, correct me if I'm wrong, but corrosion is due to inadequate packing of amalgam. In a sense,
It can be,
can it result from not enough pressure?
yeah, it can be, it
Not
can be.
having that mercury rise and
Yeah.
lead up to, so.
Yep. Okay, wettability, we talked about that with dentures. We are also gonna talk about it when we, pour stone into an impression. We also we're concerned about wettability when we're mixing cement and we're putting powder into that cement, okay? So, if it has a high contact angle, like this. This is a high contact angle, that's poor wetting. That could result in a physical change that we don't want. If it has a low contact angle, it's gonna spread, okay? And that's good wetting. So, I want my impression material, when I'm mixing it, or when I'm pouring my gypsum into my impression, I want it to flow nicely. If it doesn't, my gypsum or my stone is too thick, and I can get air bubbles, and then I have an ugly impression material that doesn't, or models, that doesn't do me a bit of good, okay? Okay, and then there's viscosity. Some materials are thin, we want it to be low viscosity, we want it to spread. Other materials, like our elastomeric final impression materials, we want them to be a little bit thicker, okay? So typically we want a low viscosity to be our cements, okay? And our higher viscosities to be our elastic impression materials, final impression materials. Okay? So one or the other, one or the other. That's viscosity. And then hardness. Okay, so you will see this on the board. Well, a lot of this stuff you'll see on the board in some way, shape, or form. But hardness is the resistance of a material into indentation. There are 3 scales out there. There's Mohs, there's Knoops, and there's Vickers. And usually the 2 you see are Mohs and Knoops. Doesn't matter what one they use. I like to do Knoops, but guess what? They all result in the same thing, okay? So, what's the hardest material in the world? Bling bling. Bling bling is the hardest material. How did you not know that? No, do you like diamonds?
I do, yeah, I do.
Okay, well, I know you like jewelry and
Yeah.
stuff. Okay, so diamonds are the hardest material in the world. So amalgam is down here, okay? It's not near as hard as a diamond, but look where porcelain is, right here. It's pretty hard, okay? And then it goes on down to composite. So, enamel, you remember that, hydroxyapatite crystals and all that jazz. Dentin, cementum, remember that from my class, what was that called? Head neck. It was like 100 years ago. And we talked about the differences, harder, softer, and softest. Well, harder is great. Enamel is very hard and brittle, so we have to have softer material underneath it, remember, to protect it. Because what if we had enamel with nothing soft underneath it? What's it gonna do? It's gonna break. Porcelain, you have to be careful. Oftentimes porcelain, we put underneath it a metal thimble, and then we coat the crown with porcelain. If it was all porcelain, what happens? Ooh, there goes my crown in my hand, okay? So we have to think about these things. We want to use materials based on chewing. Where's it gonna be? What are we gonna do? Okay, that kind of thing. So, know this, that, okay, here's another question for you. I have a tooth that's a virgin tooth. Number 3 is virgin. By virgin, I mean there's no restorations in it. It's an enamel tooth, or just a normal tooth with dent and stuff in it. And the opposing tooth is a porcelain crown. What's gonna wear? The tooth is gonna wear, because the porcelain is harder. So let's think about this. I'm gonna make a denture, and a person has their lower teeth, and their natural teeth are just fine. Now I can choose an acrylic tooth or a porcelain tooth. As a good dentist, what am I going to choose? Acrylic, because if I had a porcelain denture, what am I going to do to my mandibular teeth? I am going to pulverize the heck right out of them. Okay? So we don't want to do that.
Have you guys seen those movie stars that just get their maxillary teeth crowned and then see the lower teeth and it's like another example of that.
Yeah, pay attention. See, the more you know, the more you pay attention, and you go, holy cow. Yeah.
So I had a new patient come in once, and I'll never forget it because I don't even know how much money this person spent on their teeth. But I started doing x-rays, and when I noticed, like, their teeth looked perfect. Like, they were super white, super straight. And as I started taking x-rays, every one of their 28 teeth were covered with zirconia crystal crowns. And the guy had told me that he had like really, really bad like teeth, and he just got them drilled down and put crowns on every one of them. Now, how, I just don't understand like the benefit of that, you know? Like, I don't know.
I don't know what his teeth look like.
Yeah.
I mean, he could have had that needle,
Hypoplasia or something.
Yeah.
There could have been a reason.
or it
Yeah.
could have been a heavy grinder, and then his joint collapsed, and so they had to go back out.
So,
like $4,500 a crown.
well, we want to hope that it was for a good reason, which was treatment, and not cosmetic.
1,200, but still, times 28.
Yeah.
So if it's nice,
Yeah.
It's a nice car.
then.
Yeah. Okay, well, we want to hope that there was a good reason, and that it was need instead of cosmetic. Yeah. But we don't know that, do we? Okay, mechanical properties. So, when you bite from here to here, you lose biting power, okay? So, when patients have a denture, if they're trying to chew on those molar teeth like they chewed a steak, they're gonna get frustrated because it's only 19% of what they have. So when we make dentures for patients, we have to tell them, you know, you're gonna have to cut your food smaller, you're gonna have to chew longer. Eventually they'll adapt, they adapt to it, but at first, if they had teeth, and now they have these acrylic teeth, they're like, whoa, what's going on here? Okay, so, they have to be told that. You know, if I had a prosthetic leg, I can't walk on my prosthetic leg like a kid. You know, my biological leg. So, part of that. Stress is the ratio of force to an area. So the smaller the area where the force is applied, the greater the stress. The smaller the area, the greater the stress. So, if it's a small area with lots of stress opposing each other, and it's not spread out, you're doing more damage to that tooth if it's not being dissipated. I like to think of a high heel. If I take a high stiletto and I hit a drywall, and with the same force, it's gonna go deep. It's gonna cause a lot of damage. If I have a platform with the same force, the damage is gonna be more surface. Why? Because it's spread out. What's that?
Walking on ice.
Walking on ice. Same thing. And we don't wanna walk on ice in our stilettos. Okay, all right. So there's three kinds of stresses. There's compressive stress, there's tensile stress, and there's shearing stress. Compressive stress is when I'm biting up and down. It's the forces coming towards you. That's compressive stress. Amalgam has good compressive stress. So if it's a class 1 amalgam, you're doing the classifications, aren't you? Oh, good. Okay, if it's a class 1 amalgam, occlusal, it's got the walls of enamel, it can handle that pretty well. Amalgam has tensile stress is pulling apart. Now I have a class 2, an MO or a DO, or an MOD. Amalgam has poor tensile stress. So more than likely, a class 2 restoration is going to break on that marginal ridge. We see it all the time because over time it just couldn't resist that force. And then shearing stress is when it slides across each other. So if I'm a class 3, okay, and instead of my maxillary teeth coming over my mandibular teeth, it's class 3, you know it's the opposite, right? Well, wait a minute. Crossbite. If I have a crossbite, that's what I want to say. And, okay, so I have a crossbite. 30 overlaps 3, okay? And I decide to put an amalgam on 3, I'm probably going to break it. It's an MODB. There's no way it's going to last because of the shearing force that it can't take. Okay? Make sense?
Is that little picture wrong then? Yeah, it's switched. Yeah, I'm thinking that too. A is going away.
Well,
looks like it's pulling away.
are applied at different points towards each other. It's right. Okay? Does that confuse you? Are applied at different points, top and bottom, towards each other. What?
A has they're looking down at your so the arrows
Oh.
confusing them.
Well, dang, I took that out of the book. Yes, that's wrong. So scratch, just,
Don't pay attention to that.
I'm gonna take that off. I just put that in there. I thought it was a cool picture. Hey, that's what I get for messing around too much. It's in there somewhere. Okay, elastic modulus is the measure of elasticity. So the lower the number, modulus of elasticity, the more elastic it is. So we want impression materials to have a low modulus of elasticity, okay? So that we can take those impressions. Something like crowns and bridges and things like that have a high modulus of elasticity. So they're gonna break sooner, okay? So the higher the number, the stiffer the material. Gold would be higher than elastic impression material. Okay, the proportional limit is it, okay? That's the minimum stress that the material can stand. After that, it's gonna, it may deform and go back, but after that, past that proportional limit, it is going to break or be permanently deformed, okay? So, what do we got here? Strain. So, stress and strain go together, and I want you to look at that in your book. There's a stress-strain plot, okay? And what this shows is this. Let me just go right to it. So, this is the amount of stress that can occur, and this is the amount of strain that we put on it. You can see the modulus of elasticity is a lower number, like impression material. But if we go too much then we go past that elastic limit, we're gonna have deformation. If we go too far, but it is probably we're gonna have some deformity. We go too far, we're gonna have failure, okay? Ultimate strength is failure. Ultimate strength is failure. Note to self, ultimate strength is failure. Okay. Yield point proportional limit or elastic limit is its minimum deformation. Now, let's look at the amount of strain, okay? Impression material. We can put a lot of strain on it before we get to this or this, okay? A ceramic crown, it doesn't take much strain to break that baby, right? It's exceeded its strength and it's going to fail. Old crown, kind of right in the middle there. But it can get to a point where we've made mincemeat out of it too. Okay? Stress strain plot, please make sure that you know that. And I think I'm getting close to the end here. Am I? No.
Nope.
You guys doing okay?
It's a lot, it's overwhelming, but it's basically key terms that will help you.
Resilience and toughness. What I want you to remember is resilience is the ability to absorb energy of baseball to the mouth without deforming. Mouth guard material, which we put on a maxillary arch, can deform. It's able to get that resilience, okay? To absorb that energy so that those teeth underneath don't break. Toughness, it's a little bit more. Mouth guard on the head riding a motorcycle isn't going to help you if you have a crash. You need something a little tougher than that, okay? Might look stupid too. Okay, so other properties that are time dependent. Fatigue, materials weaken over time because of stress and strain. Okay, did one of you wear a mouth guard on your head?
I'm like picturing you just walking around with that guard.
I don't know why I find that so funny.
Sturgis, right? Here I come with a mouth guard. Okay, so and that's called fatigue. They get tired, and then, you know, that material needs a little walker. And then when things get too tired, like amalgam, they creep over the surface of the margins, okay? And when that amalgam creeps over the surface of the margins, they break, then we have marginal breakdown. Marginal breakdown, let me go back to corrosion and tarnish. By nature, and we have marginal breakdown, it's uglier than sin, but we don't need to replace it unless there's decay. Or it's just so open the tooth has too much sensitivity. What happens is when the tooth corrodes, the corrosion products fill in the crevice, and that's ugly too, but it protects the tooth. Okay. So where is two surfaces coming together, attrition and abrasion? You guys know all about that. These two terms, I see them on the board test study guide, and I don't know what to do but memorize it. Ductility is a material that deforms because of tensile load, pulling apart. Malleability is compressive load. I don't know how to memorize that, except, or miss it. Take that.
I chose gold in my mouth because of its malleability, because of my stress and how I might punch. So think of it as a softer material in that aspect.
That's compressive, yeah?
Yeah, that might help you. And like you can roll your margins back and then let it open.
Okay, solubility, dissolving in liquid. We all know what that is. Absorption absorbs water. I think we know that. Color is our response to a stimuli, and abrasiveness is wearing away. Okay, so now we're getting to chemical properties. We're getting there. Gypsum sets via a precipitation process. That is a chemical process, okay? I mix water with this powder and it changes into a different substance, okay? Biologic properties, it shouldn't have an effect on living tissue. It shouldn't be toxic. So, let me point out to this. This is acrylic. This isn't the strongest denture in the world. It's definitely compatible. This is a better denture with the metal, okay? It doesn't rock as much. It's a much better. We're covering up not as much tissue as we are with this. But what do we have to be careful of with this metal? It has to be strong. So you'll hear 10 weeks from now something about non-precious metals, okay? Because they're strong. It doesn't want to, we don't want nickel in this because people are highly allergic to nickel these days and have been for the last 15 years, okay? And with ortho, our wire has to be compatible as well. So we have to have a material that is not toxic. So when we have it, the working time is the time I have my impression material, I pour in the water, I mix it up, and it's getting thick. That's my working time. I have to get it in the tray and in the mouth because I'm running out of working time. My setting time is I put my water into the material, I stir it up, I put it in my tray, I put it in my mouth, and when it is done cooking, ding, I take it out, okay? So, except the alginate doesn't go ding like your oven does. Okay, so what you want to do is whenever you get a new material and you haven't used it, read the directions. I don't care if it's the same material, it handles differently. Just like when you buy a box of brownies, right? They all handle differently. Materials set faster in the warmth of mouth or in the humidity of a room. So, that hot summer day, like today, when we can't control the heat in the dental office, we are going 95 miles an hour to get things mixed and in the mouth before they set up. Oh, and it gets even worse when your air conditioner breaks. Dispensing materials is equal lengths, not volume. So see this? This isn't volume, it's equal lengths, okay? With drops, we have to be consistent. We can't be sloppy if we're using drops, and we have to fluff powders. We are going to have a break here real soon because you guys need it. And mixing, always mix aggressively. You don't want to go teeny, okay? You really want to mix that thing to incorporate that powder into that liquid, okay? So it does its job. So forcing it into the liquid, and your setting rate depends on how you mix. And so you want to do it right because cements particularly have time frames. When you use light activated materials, I want you to know that you can never over-cure. So if you over-cure too long, no big deal. If it's not long enough, it's a big deal. Okay, a soft composite, a soft sealant, or whatever. And this is it, the bottom line. You get a break. To function properly, a restoration must be hard, strong, that's yield strength, and stiff, elastic modulus. It's a high number to withstand the forces of mastication. Dimensional stability is an important property of impressions and restorative material. We talked about that, right? Okay. And thermal conductivity is important because too much hot and cold to the pulp, what can happen? Ouchie wawa. Now I've irritated the pulp so much I have an abscess. Holy cow. It's all my fault. All right. We are taking a 10-minute break.